almost every programming language, like MATLAB or C or anything, gives you a way to sample uniform distributions. So I'm not going to discuss how the computer does that. There is actually a pretty interesting, a set of pretty interesting algorithms that generates what's called a pseudo-random numbers, that are numbers that are, I mean, if you look deep into the generation mechanism, it's actually not really random, but the numbers that it generates behaves in almost every way like a true random number, so that we can, for all practical purposes, for almost all practical purposes, we can consider that as a true random numbers. And usually it is given as random numbers satisfying a uniform distribution between 0 and 1. And sometimes a uniform distribution between 0 and some maximum number. All right, so what we really want to discuss in this lecture is what if the input parameter, what if the input random parameter that describes your differential equation or initial condition is not uniform? What can we do to sample numbers like that? Okay, so the first method I'm going to be using an example of a triangular distribution. The triangular distribution is mostly easily characterized by the PDF, or the probability density function of the random variable x. It is called a triangular distribution because the PDF is actually a triangle, like that, right? Something very similar to the kind of nodal basis function we use in our finite element methods. So the PDF starts at A, okay? It peaks at a value B and it goes back to 0 at a third value C. So maybe somebody can tell me what should the peak of the PDF be? Like, what is this peak of the PDF? How do you know the peak of this PDF? Anybody? Don't have to give me answers, but like give me, how do you figure this out?
You need the area of the triangle to equal 1.
Yes, the area of the triangle, which is the integral of the PDF, has to be 1, right? Because the PDF is going to be the derivative of the CDF, and the CDF is equal to 0 when x is minus infinity and equal to 1 when x is plus infinity. So the integral has to be 1. That means the area below the triangle, which is C minus A, times the height. So if this is the height, has to be equal to, well, divide by 2 because it's a triangle, has to equal to 1. That means my height has to equal to 2 divided by C minus A, right? So this is 2 divided by C minus A. So the question is, how do we sample from that? And to this end, I want to introduce the method of acceptance rejection method. So this method depends on the fact that you can sample another distribution whose probability density function could kind of at least a scaled version of that probability density function would be strictly would be greater or equal to the PDF of the desired distribution. For example, for this triangular distribution, we can easily construct a uniform distribution, right? Like that. Well, of course, the uniform distribution between A and C would have a height that's half as big as that of the triangular distribution, but that doesn't matter. As long as you can scale it with a finite value, in this case 2, once you scale it by a factor of 2, the uniform distribution would have a PDF that's at least as big as that of the triangular distribution. We are fine. Okay, so we start from uniform AC. So basically, we are going to be sampling the uniform distribution between A and C. And then we get a bunch of x1, x2, etc., up to xn. Right? Of course, this is not going to be a triangular distribution because these axes are equally likely to be very close to C as they are around B. But for this to be a triangular distribution, I need the samples to be more likely when it's around the B and less likely when it is around the C and A. So how do we kind of change these values to make them what we want? The idea of this method is to either accept or reject this set of samples depending on where they are. Okay, this is basically if I have a particular xn, for example, xi, that's here, I'm going to be looking at the height, and I'm going to be sampling another independent random variable. Let me call it yi. Okay, so let me just call it yi. So I'm going to be sampling the yi. For example, it might be here, it might be here, it might be anywhere between this and this, right? I'm going to be also sample y1, y2, etc. to yn according to another uniform distribution that's from 0, let's see, 0 to h, right? Because h is the highest PDF we have over here. Okay, and the idea is that if the sampled y lies above the PDF of the desired distribution, I would be rejecting that x. And I'm only going to be collecting a particular xi if the sampled yi turns out to be lower than the desired distribution. So I'm going to be accept xi if and only if my yi is less than the PDF at xi. Okay,